continue on talking about the three-body problem. And in the tri-solar system, the weather and the ecological stability of the trisolarian system was very disrupted because the three stars were acting up. And you can imagine how complicated the weather would be if we had three suns that were relatively close to each other. One of the things that they found attractive about the Earth was it would be a nice stable system that they could move their civilization to and be able to live in a benign environment. So the issue is, how likely is that to be an issue? And the answer is, it's pretty likely. A good fraction of the stars, roughly half the stars, are either in binary systems or trinary or even more systems, although the stars are not usually very close to each other. But if we go back and address the question of how long do stars last, we know from careful study and from observations that a star like our sun lasts about 10 billion years. And it burns very stably and very reliably for almost 9 billion of those years. It's a very nice, stable environment. It slowly gets warmer at the end, and then it grows into a red giant, and that becomes really untenable for life on the Earth. So if humans still exist, they have to be able to move from the Earth within 4 billion years from now. But it will actually start getting noticeably warmer in about 1 billion years. And so it's something that as humans, we may have to pay attention to. We have to make it through the next phase, but we'll see. So it's easy to make a simple model to understand how things go. If a star is more massive, it has more gravity. That makes it denser and hotter in the beginning, and it increases the rate of burning. It increases the rate of burning in such a way that the star will actually burn up with about the 4th power more quickly. So a star that's 10 times as massive as the sun will burn out by that formula at about 10,000 times faster. So if the sun was to do 10 billion years, it will be 1 billion years, but actually the lifetime is more complicated because it's beginning phase and then end phase and so forth. So it's on the scale of 30 million years, but it's still the 10 million to 1 million sort of estimates you'd get from this kind of calculation will give you that. Now the fact is, stars vary a lot in how much mass they have when they come together. Not a huge amount, but it varies. And so you can actually look at the stars in a galaxy and they form what's called a main sequence. They're stars that are, if you make a plot of their temperature versus their very brightness or whatever it is, you find this nice steady line, and then it rolls over and does this kind of stuff. Now astronomers plot everything backwards, so it's a funny kind of thing because of the units they use. But the fact is, we know there's a whole range of stars, some that are very low mass stars that will last 100 billion years in the extreme case. Most stars that are still around now, or like our sun, they're sort of in the 10 billion year range, but plus or minus, a couple of billion years. But there are some stars that burn very fast, and we think the very first generation of stars had some different ranges, and the very massive ones, they burned up very quickly, and they ejected their material, and they made the heavier material, and that allows us to make the heavy elements and the rocky planets and so forth. And so it turns out to be very important for us that the first generation of stars actually process things quickly. So 60 solar mass stars, they're done in 1 million years, kind of time scale. They then eject all this material, including the hydrogen and helium they've burned to the heavier elements, and that allows you to form planetary systems and so forth. And so it's actually important that they burn very quickly and very fast. It also means you don't see so many of them around unless there's star-forming regions. In our own galaxy, we see them in new star-forming regions, places like the Orion Nebula, where stars are just forming out of big dust clouds and gas clouds, or in the leading edge of the spiral arms. That's where you see the leading edge looks so bright because it has some of the very massive stars. So you have this tremendous range in the lifetime of stars, and just like we know the Earth is a second generation star system. We see that because we can see the heavier elements, we can see the stuff the Earth is made out of, And we can look, there's some uranium and some other heavier elements, we can look and radio date these things, and that's how we know it's 4.55 billion years, and we can see what it is. And we even understand that probably we had a star that exploded first and spread out all this new material, and then another one went off not so long after that one expanded and cooled. And the shock wave from the second star caused the collapse of the solar system, which caused the planets we see. And the inner planets are only the rocky planets, because you have to get out to Jupiter distance. When you get out to Jupiter distance, then you have the frost line. That is, water can be condensed, and that helps make a much heavier planet. So the heaviest planet is Jupiter, and the next heaviest Saturn, and so forth. Those gas giants are caused by the addition of water to their system. So we know quite a lot, but what it tells us is, because these big massive stars can come so quickly, there can be planetary systems that formed 10 billion years ago as opposed to 4.5 billion years ago. The lifetime of stars is so varied and so changed, it's hard to predict. And when you put them together in a complicated system, if they're close together, they can actually feed each other and, in fact, feed material back and forth to each other and affect each other. So the lifetime of stars is extremely varied, and most of the situations are fairly stable, and it's good for the forming of habitable regions.